Welcome viewers to the sixth and the last segment of the online series of lectures for the course of linear algebra. In the previous segment, we stated Theorem 8 and proved it. Let me recapitulate the statement here. In Theorem 8, we had two finite dimensional vector spaces V and W defined over the same ground field F, defined over F, um, such that dimension of V is equal to dimension of W. We started with a uh, linear transformation T from the vector space V to the vector space W. And we had the following three statements to be equivalent. The first statement was that T is invertible. Then the second statement is that T is non-singular, and three is that T is onto, that is, the range of T is the whole of the vector space W. These three statements are equivalent. Okay, so in this segment, we will try to give two more statements that are equivalent to all these three statements. So let me write them here. There are two more conditions that are equivalent to the three conditions stated above. Um, Number 4 is that if U1, U2, all the way up to UN is a basis for the finite dimensional vector space V, then TU1, TU2, all the way up to TUN is a basis for the vector space W. That's condition 4. And condition 5 states that there is always such a basis. There is some basis U1, U2, all the way up to UN for V such that TU1, TU2, all the way up to TUN is a basis for W. Okay. So the only difference between 4 and 5 is that 4 does not state the existence of such a basis of the vector space V, whereas 5 does. 5 tells us that there always exists such a basis of V, so that T applied to each vector of that set um, you know will be an element in the basis of the vector space W. Okay, right. So now we will first prove that 3 implies 4. this 3 implies 4. Okay, so let's do this. Let me erase everything here and prove that 3 implies 4. We assume that T is onto. That was the third statement. T is onto. We now have to prove that statement 4 holds. Let the basis of U1, U2 all the way up to UN, let this guy be a basis for V. Now, given W in the vector space W, okay, there always exists a vector V in the vector space V such that T acting on V is equal to W. This is always possible. There always exists such a vector since T is onto. Since T is onto, according to the hypothesis. Okay. Therefore, the vector W is equal to T acting on the vector V, right? And the vector V can be, basis expanded in this basis. Since vector V is an element in the vector space V, and this is a basis for the vector space V. So let us write vector V in terms of the vectors here. Let us write vector V as a linear combination of these vectors appearing in this basis set. Okay, let where C1, C2 all the way up to Cn are the coefficients of the underlying linear combination. Okay, okay, and since T is linear, we can always write it as C1 TU1 plus C2 TU2 plus all the way up to Cn TUN. Okay, yeah, since T is linear. Now any vector W in the vector space W can be written so from this expression we can see that any vector W in the vector space W, we started with that vector in the vector space W, and it turns out from this expression that any vector W can be written as a linear combination of the vectors in the set TU1, TU2 all the way up to TUN. Okay, like we are seeing here. Okay, so which means that this vector space W is the span of these n vectors TU1, TU2 all the way up to TUN. Okay, since dimension of this vector space W is the same as the dimension of V, Okay, and we have chosen this set to be a basis of V, implying that dimension of V is equal to n, and hence dimension of W is equal to dimension of V is equal to n. Okay, so we arrive at the fact that dimension of W is equal to n, and this fact forces this set to be a linearly independent set. Therefore, TU1, TU2, TUN is linearly independent. Okay, since this set has n many vectors, this set has to be a linearly independent set. Therefore, so this is a linearly independent set in W, and this set spans W, which means that this set consisting of n vectors is a basis for the vector space W, okay, which we needed to prove to satisfy condition 4, right? Now we are going to prove that the condition 4 implies condition 5. Condition 4 implies condition 5. Now, since V is a finite dimensional vector space, it has a basis comprising of dimension V many elements. Right? It has a basis comprising of dimension V many elements in it. Let this finite dimensional vector space has dimension to be equal to n. Denote a basis which always exists, we know from the theory of vector space, which always exists. So denote a basis of the vector space, finite dimensional vector space V by U1, U2, all the way up to UN. Okay, so the only task here was to establish that such a basis exists. Now by condition 4, TU1, TU2, all the way up to TUN is a basis for the vector space W. Okay, so this is what we needed to prove for condition 5. Right? Now we need to prove that 5 implies 1. Okay, 5 states that there always exists a basis U1, U2 all the way up to UN of the vector space V such that TU1, TU2 all the way up to TUN is a basis for the vector space W, right? That's condition 5, and we need to prove that this condition will imply that T is invertible. Okay, Okay, so let's start with the hypothesis, which is the you know which is the fulfillment of the condition 5. Suppose there is some basis um, given by u1, u2 all the way up to un of the vector space V such that tu1, tu2 all the way up to tun is a basis for the vector space W. Okay, now from the definition of a basis, uh, we know that this set spans W. Hence, the set tu1, tu2, all the way up to tun spans W. That means given a vector W in the vector space big W, there exist scalars Ci in F with I lying between 1 and n such that the vector W can be written as a linear combination of these vectors. So let us write this linear combination C1 TU1 plus C2 TU2 plus all the way up to CN TUN. Okay, we can always do that. So now we apply the linearity of the transformation T to have it written as a T of C1 U1 plus C2 U2 plus all the way up to Cn Un. So since T is linear. Okay, and well, we write it as T acting on a vector V, right, where a vector V is given by the linear combination of these n vectors, where V is equal to C1 U1 plus C2 U2 plus all the way up to Cn Un belonging to the vector space V, right? So let me erase this top part here. Okay, so we have been able to show that given a vector W in the vector space W, we can always find a vector, always find a vector V in the vector space V such that T acting on that vector V is equal to W, right? Which means that the range of the linear transformation T is the whole of the vector space W. In other words, T is onto. Hence, T is onto. Okay, so we started with the condition 5 and we ended up proving that the linear transformation T from the vector space V to the vector space W is onto. Okay, now we are left with proving that T is also non-singular. and that will prove that T is invertible. Okay, so let's prove that it's non-singular. If a vector V is equal to C1 U1 C2 U2 plus all the way up to Cn Un is in the null space of the linear transformation T, right? So we choose this vector in the vector space V to be in the null space of T or kernel of T. Okay. So then if this V is in the null space of T, or we can write it as V belonging to kernel of T, if this holds, then of course T acting on V gives the zero vector of the vector space W, right? So that we have T acting on this vector C1 U1 plus C2 U2 plus all the way up to Cn Un is equal to the zero vector of the vector space W. That implies using linearity of the transformation T from the vector space V to W, C1 C1 T U1 plus C2 T U2 plus all the way up to Cn T Un is equal to the zero vector of the vector space W. Now, according to the hypothesis, or in other words, according to statement 5, or according to the condition 5, we know that this set TU1, TU2 all the way up to TUN is a basis of the vector space W, right? And since this guy is a basis, it is a linearly independent set. And we are assuming an arbitrary linear combination. No, it's not an arbitrary, but for any, we are setting a linear combination of these n vectors in terms of this coefficient C1, C2 all the way up to Cn to be the zero vector of the vector space W. And since this is a linearly independent set, we must have all these coefficients of the linear combination to be identically zero. Follows from the linear dependence of this set TU1, TU2 all the way up to TUN. Okay, so we know that this is equal to V, and it implies that the vector V is equal to the zero vector of the vector space V, since all these coefficients in this linear combination are zero, identically zero. Therefore, vector V is the zero vector of the vector space V. Okay. So, what is kernel of T? Therefore, kernel of T, so we chose an arbitrary vector in the kernel of t, and we ended up with the fact that that vector v is the zero vector of the vector space V, which proves that kernel of T is trivial. That is, uh, it is a singleton containing the zero vector of the vector space V only, and hence T is non-singular. So we have been able to prove that T is onto, and we also proved that T is non-singular, meaning that T is one-to-one, and hence T is invertible. T is invertible. Okay, so QED. This proves that these 5 conditions are equivalent. The first 3 conditions were stated and proved in the previous segment, and in this segment we proved that condition 4 and condition 5 are also equivalent to those 3 statements. In particular, we proved that 3 implies 4, 4 implies 5, and 5 implies 1, which means that all these 5 statements are equivalent to each other. Okay, so now uh, the terminology of a group that follows from what we have discussed so far about invertible linear operators on a vector space V. The set of all invertible linear operators on a vector space V with operation of composition So now we are restricting our attention to the invertible linear operators. It's not the whole set of linear operators on a vector space, which is endowed with the structure of linear algebra. We are, on the other hand, concerned with the subset of linear operators on the vector space V. Okay, invertible linear operators, the subset of invertible linear operators on the vector space V. That's what we are concerned with. With the operation of composition is an example of the algebraic structure called a group. Okay, so here goes the definition of a group. A group consists of the following data. Okay, the first thing is a set G. Secondly, an operation denoted by dot, which associates with each pair of elements x comma y in the set G, an element x dot y in the same set G in such a way that this operation is associative, meaning that x dot y dot z is equal to x dot y dot z for all, this is A, for all x, y, Z in the set G. B, there is a distinguished element called a unit. There is a distinguished element E in the set G such that E dot x is equal to x dot E is equal to x for all x in the set G. Okay, E is called, this distinguished element E of G is called the identity element. Okay, C, to each element x in G, there corresponds an element x inverse in G such that x dot x inverse is equal to x inverse dot x is equal to the identity element, that distinguished element E of G. Okay, and this x inverse is called the inverse of the element x. Now I want you to verify that the set of all invertible linear operators on a vector space V with the operation of composition is indeed a group. Okay, I want you to verify this. Okay, so we thus see that the subset of the linear algebra of linear operators of on a given vector space V is can be endowed with the structure of a group. Okay, so you have the linear algebra of the linear operators on a vector space. Okay, and you take the subset of the invertible linear operators on a vector space, and you see that it's endowed with the structure of a group. Okay, so now I suggest you some exercises from our textbook. So let me list the problems here, suggested exercises. Page number 83, problem number 1, number 2, number 3, number 5, number 10, number 11, and number 12. Okay, so that's all about lecture 7. In lecture 8, we'll study representations of linear transformations from a vector space to another vector space W over the same ground field F. Okay, so we have this vector space of linear transformations from a given vector space V to another vector space W, both defined over the same ground field F, and this is an abstract set. Okay, but we want to realize these linear transformations as matrices. Okay, So these are called representations of the linear transformations from the vector space V to the vector space W. So we'll uh, um, study the representations of linear transformations from a given vector space V to another vector space W over the field F in the next lecture. Okay, thank you for attending in the 7th lecture.